Section: Introduction. In this section, we discuss the growing importance of on-device language models in our connected world, highlighting their benefits like improved privacy, lower latency, and offline capabilities. However, we face challenges with energy consumption and processing speed, especially when dealing with long contexts. Battery life on mobile devices is a major concern, as complex language tasks can quickly drain power, limiting the effectiveness of on-device AI. This issue worsens with longer contexts that demand more computational resources and memory. Additionally, the delay caused by processing large inputs can negatively affect user experience in real-time applications like voice assistants and chatbots. Therefore, we urgently need innovative solutions that maintain the accuracy of language models while reducing energy use and improving response times. To tackle these challenges, we have seen various strategies aimed at addressing the context length issue in large language models. One notable approach is Retrieval Augmented Generation, RAG, which adds an external retrieval component to find relevant information, allowing the model to manage extensive knowledge without needing to store everything internally. Recent developments, such as the long RAG framework, have enhanced this method by distributing the workload between the retriever and reader, enabling the processing of larger input sizes. Another effective strategy involves optimizing the key-value cache. Techniques like chunk-wise cache compression and swapping help reduce the overhead of context switching and maintain efficiency across multiple uses. The Language Models as a Service (LLMaaS) model exemplifies this by integrating language models as system services on mobile devices, using stateful execution to keep persistent states and lower memory usage. While these methods show promise, they often require trade-offs between context length, model performance, and computational efficiency, indicating a need for more comprehensive solutions. Some research has focused on directly reducing context length to cut down on computational costs. Although these methods aim to compress context, they can introduce their own overhead and may not align well with the original text. In response, we introduce Dolphin, a new decoder-decoder architecture designed for energy-efficient processing of long contexts in language models. Inspired by recent advancements in vision language models, VLMs, we utilize a smaller decoder to distill extensive contextual information into fewer memory tokens, significantly shortening the input for the main decoder model. By treating long text contexts as a separate modality, we can process much longer inputs without the usual computational burden. This results in a 10-fold improvement in energy efficiency and a 5-fold reduction in latency compared to traditional methods. Our work contributes to the development of more sustainable and scalable language models for on-device applications, addressing the urgent need for energy-efficient and fast AI technologies in resource-limited settings while ensuring accuracy in understanding long contexts. This advancement has significant implications for deploying advanced AI capabilities on edge devices, potentially transforming areas like mobile computing, IoT, and wearable technology. We also explore prompt compression, which has become essential for managing long context inference in large language models. Current methods fall into 3 categories: token pruning, abstractive compression, and extractive compression. Token pruning techniques aim to shorten prompts by removing less important tokens. Abstractive methods condense the original context through summarization, while extractive methods select relevant parts from the original text. These can be query-aware or query-agnostic, depending on whether they adapt to specific tasks. Additionally, some works focus on compressing or distilling context to lower computational costs. For instance, autocompressor compresses long contexts into summary vectors, while other methods modify attention mechanisms to extend context windows. Despite the growing interest in prompt compression, there is a lack of standardized analysis comparing different methods, making it difficult for practitioners to choose the best approach for their needs. Our work aims to fill this gap by providing a thorough evaluation of various prompt compression techniques across different tasks and compression rates. We also discuss multimodal large language models, MLLMs, which enhance traditional models by processing multiple types of data simultaneously. MLLMs consist of a modality encoder, a projector, and a language model. The modality encoder handles different data types, while the projector aligns these with the language model, allowing for a unified representation. The development of MLLMs typically involves pre-training individual components followed by integration through further training with mixed data. Finally, we address the deployment of on-device models, which is crucial for efficient execution across various hardware platforms. Frameworks like Llama.cpp and MNN optimize inference on local devices, while edge cloud frameworks enable flexible deployment options. These strategies collectively improve the feasibility and performance of on-device language model deployments, catering to a wide range of applications and hardware constraints. Section Summary. In this section, we discuss the challenges and innovations in on-device language models, particularly focusing on energy consumption and processing speed when handling long contexts. We introduce our novel Dolphin architecture, which significantly improves energy efficiency and latency by distilling extensive contextual information into memory tokens, thereby enhancing the practicality of AI applications on resource-constrained devices. Section: Methodology. In this section, we outline our approach to developing the Dolphin model for efficient long-context processing. We introduce a new decoder-decoder architecture, implement memory tokens, describe our multi-stage training process, and detail the dataset used for training and evaluation. These elements work together to tackle the challenges of energy efficiency and latency in on-device language models while ensuring the ability to understand long contexts. We conceptualize long context as a new modality in our model design. Our architecture features two decoders of different sizes, a smaller decoder, which we refer to as pi_s, with 0.5 billion parameters, and a larger decoder, pi_l, with 7 billion parameters. The smaller decoder transforms information from the extensive context, while the larger decoder focuses on understanding and generating responses to the current query. The text encoder we use is based on transformer decoder architectures, specifically derived from Qwen 2.0.5b, while the main decoder is based on Qwen 2.7b. During inference, we process the user's query in the context, where the query is typically much shorter than the context, as seen in multi-round conversations or retrieval augmented generation scenarios. Similar to vision language models, we use a projector to convert the embedding information from the text encoding into context token embeddings suitable for the main decoder. This projector is a multi-layer perceptron that connects the different embedding dimensions of the text encoder and the main decoder. For the text encoder, we utilize Qwen 2.0.5b, which transforms the context into an embedding representation for further processing by the main decoder. If we were to send the context directly to the main decoder, the embedding size would be proportional to the context length multiplied by the decoder's embedding size. By first passing the context through the smaller decoder, we reduce the embedding size, achieving a compression rate that can reach up to 8 without losing response quality. This architecture allows us to efficiently process long contexts, treat them as a distinct modality, and adapt easily to various tasks involving long contexts. To enhance information extraction from long contexts, we introduce memory tokens. We augment the tokenizer with special tokens that capture a latent representation of the long context. By appending these memory tokens to the original context, we create an augmented context that we then process through the text encoder. The resulting embeddings corresponding to the memory tokens provide a condensed representation of the long context, improving our model's ability to manage long-range dependencies while reducing computational demands. Our training process for the Dolphin model consists of 3 stages: restoration training, continual training, and instruction fine-tuning. This multi-stage approach is designed to progressively improve the model's capability to handle long contexts and generate suitable responses. Section Summary. In this section, we outline our methodology for developing the Dolphin model, which includes a novel decoder-decoder architecture with 2 decoders of different sizes to efficiently process long contexts, the introduction of memory tokens for better information extraction, and a multi-stage training process to enhance the model's performance in handling extensive contextual information. These components collectively aim to improve energy efficiency and reduce latency while maintaining robust long-context understanding capabilities. Section: Restoration Training. In this section, we outline our training process for the model, which consists of three main stages: restoration training, continual training, and instruction fine-tuning. During restoration training, we concentrate on the model's ability to reconstruct information from compressed data. We start with the context, compress it using our text encoder and projector, and then train the main decoder to restore the original context from this compressed version. Our goal is to minimize the difference between the restored context and the original, ensuring effective reconstruction. We can also use special tokens or prompts to guide this restoration. In the continual training stage, we enhance the model's ability to generate coherent continuations of partial contexts. We split the context into two parts and train the model to generate the second part based on the compressed representation of the first. Here, we aim to reduce the gap between the generated continuation and the actual continuation, improving the model's contextual generation skills. Finally, in the instruction fine-tuning stage, we refine the model on tasks that require following instructions. Given a context and a query, the model learns to produce an appropriate response. Our objective is to minimize the difference between the generated response and the correct one, thereby improving the model's relevance and accuracy in responding to queries. We also compare our approach with vision language model training, specifically with LLAVA. While both methods involve multi-stage training, our focus is on long textual contexts, whereas LLAVA integrates visual and textual information. Both approaches aim to enhance the processing of multimodal inputs and generate contextually relevant responses. For our Dolphin model's training and evaluation, we created a diverse dataset tailored to each training stage. We gathered 100,000 context samples for the restoration training from various domains to ensure broad coverage. For continual training, we used another 100,000 distinct samples to help the model learn coherent continuations. In the instruction fine-tuning stage, we employed a comprehensive dataset of 1 million question-answer pairs with relevant contexts, covering a wide range of domains and varying in length and complexity. To ensure quality and diversity, we utilized several high-quality existing datasets, including the pile, natural questions, book corpus, and scientific papers from arXiv. For our experiments, we used a testing dataset of 3,740 samples from the prompt with context dataset, focusing on contexts shorter than 512 words. The questions in our dataset fall into 6 categories: contextual QA, numeric QA, rephrasing, summarization, title, keywords, and continuation. We designed our testing experiments to cover all 6 categories for a thorough evaluation of the Dolphin model. We first assessed the model's auto-encoding performance during the initial training phase, focusing on its ability to accurately restore text after compression. This is vital for maintaining meaning in later tasks. We present an example showing the model's high restoration accuracy, with only a minor difference between the original and restored texts, demonstrating its capability to preserve semantic integrity even with less common vocabulary. Section Summary. In this section, we outline our multi-stage training process for the Dolphin model, which includes restoration training to reconstruct compressed information, continual training for generating coherent context continuations, and instruction fine-tuning for accurate query responses. We also describe our comprehensive dataset, which consists of 1.2 million samples across various domains, and detail our evaluation methodology using a diverse set of testing questions to assess the model's performance in restoration and contextual understanding. Section: Compression Performance. In this section, we evaluate the Dolphin model's latency and compression quality against other models. We conducted all experiments on a single NVIDIA A180GB GPU using the Microsoft Azure Cloud Platform. To measure latency, we used the Qwen 2-7B model as a baseline, while the Dolphin model utilizes 2 decoders, Qwen 2 to 0.5B for generating compression tokens and Qwen 2 to 7B for processing. Our results show that the Dolphin model is significantly faster, with an average latency of 4.32 seconds, which is about 4.79 times quicker than the Qwen 2 to 7B model's 20.71 seconds. This efficiency is largely due to our decoder-decoder architecture, which effectively manages long contexts with less computational load. For assessing compression quality, we used GPT-4 to evaluate the accuracy of responses based on the input prompt. The Dolphin model achieved perfect accuracy in the title, keywords, and continuation categories, and high scores in others, such as 97.76% for contextual QA and 98.53% for numeric QA. Notably, it exceeded 98% accuracy for numeric questions, which require precise values. These results indicate that the Dolphin model not only reduces latency but also maintains the correctness of outputs across various tasks. We also compared the Dolphin model with Auto Compressor, based on Llama 2 to 7B, and Qwen 2 to 7B. Our findings suggest that Auto Compressor may overfit its training data, while Dolphin shows consistent performance. Despite using compressed tokens, Dolphin performed comparably to Qwen 2 to 7B, winning 23.6% of comparisons and tying 44.2%, resulting in a combined win-tie rate of 67.8%. This is significant, as compression models often experience performance drops. Our results indicate that Dolphin's compression techniques effectively maintain and even enhance Qwen 2 to 7B's capabilities while reducing computational needs. Overall, the Dolphin model's superior performance in both latency and accuracy highlights its potential for energy-efficient language modeling, especially in resource-limited settings where speed and accuracy are essential. These findings suggest that our architecture provides a promising solution for applications requiring fast and accurate natural language processing.